my pleasure to introduce Camila Sehnem from University of Waterloo and Kyoto University RIMS, who will talk about nuclearity for Toeplitz algebras associated to product systems.
Thank you for the introduction, and thanks to the organizer. I really participated. It's been very nice, and especially thanks to Ethan, who's been been a lot of work. And so I mentioned, I'll talk about societal associated to correspondence. They didn't appear very much, but just myself. So we start with a fixed algebra. And a right Hilbert model is a generalization of a Hilbert space, but you have a right action and you have an inner product with values in the C-star algebra, which is compatible with this right action. And a correspondence is over A is a right Hilbert model, which also has a star homomorphism into the adjoint. And we can also talk about compact operators of a correspondence, which are generated by generalized weight. So I find standard time rank. Examples: cross a Hilbert space. It's a correspondence over complex numbers. And one example that is very important and motivating for me is if you have a universal system algebra and you consider an endomorphism which is injective and has a time range, then we can form a correspondence over A. Our underlying space is A multiplied by the projection on the right, and we use the inverse to define the inner product. So this makes sense because we know the range is hereditary, and the left action is just multiplication, and the right action is implemented by the endomorphism. So, and this gives a correspondence over A. But actually, if you remove this assumption of faithfulness and hereditary range, you still have a correspondence, but then you put the projection on the left. The reason I usually consider this case because most of the examples of integers you have this property, so that's a range and faithfulness. And there are also correspondence coming from graphs and other range of other examples. Now, how we want to attach C-star algebras coming from this correspondence. So we define another correspondence over A, which is now the direct sum over all the n-fold balanced space of products over A. Right? For n is equal to 0, we just regard A as a correspondence over it. And we define a map from E into the adjoint operators of this Fock space, and also from A as just the diagonal left action. And the Toeplitz C-star algebra of the correspondence is then the C-star algebra generated by the image of A and E inside the adjoint operators on the Fock space. And you can also describe the Toeplitz algebra as via universal properties, is universal for representations of the correspondence, meaning that we have a maps from A into a C-star algebra B, which is star homomorphism, and a linear map from E into B, and this pair preserves the structure of correspondence, left and right actions and linear product. And there is always a gauge action on the Toeplitz algebra, which fixes the coefficient algebra and just acts on the correspondence itself. And this gives to the Toeplitz algebra a nice grading over the integers. So meaning that we have a subspace for each n, and the multiplication and involution are compatible with the operations of them. And hence, we also always have this space of conditional expectation onto this fixed point algebra. And the Queen space algebra, which maybe is more popular, is defined as a quotient of the Toeplitz algebra by a second invariant ideal. In general, the Toeplitz algebra may have many ideals. It's not simple, but the Kuhn-Space algebra is really what works as a cross product and codes the correspondence in a nice way and is often simple, for example. And in particular, we always have the gauge action, the central gauge action on the constraints algebra. So for this talk, I will focus mainly on the Toeplitz algebra, and I'm looking at nuclearity. But the constraints algebra is also always a quotient, and hence the results will apply also for constraints algebra. Some examples: if we view C to the n as the Hilbert space as a correspondent over C, then the Toeplitz Kunz algebra, the Toeplitz algebra, this corresponds is just the Toeplitz extension of the Kunz algebra. So it's just the system algebra by any isometry with mutually orthogonal range projection such that this product is zero, as Marcelo mentioned before. And when you do the Kunz algebra, then this is just the Kunz algebra, which is that simple. And now if you take again, L2 is the Hilbert space, and the Kunz algebra is the same as the Toeplitz algebra, it's on the Kunz. And if you take an injective endomorphism hereditary range, which could be, for example, an automorphism, and this gives the semigroup cross product when you take the constant algebra. And you can also recover graph system algebras from correspondence. These are some examples. And so result of Katsura. So we always have a conditional expectation from the Toeplitz algebra into the coefficient algebra. So we can go a little bit further. And hence, nuclearity of the coefficient algebra is equivalent to nuclearity of fixed point algebra for this gauge action, which is also equivalent to nuclearity of the Toeplitz algebra. So whenever we start with some nuclear system algebra, then we have a nuclear Toeplitz algebra. And I will just briefly mention how the proof goes, because in the more general setting, this is the base calculus. So you just, for each n, you consider the compact operators on the input tensor power plus the correspondence. And for each n, you consider the sum from k equals to 0 and to n of these compact operators. This will be a C-star algebra. And for n, if you consider compact operators of the n plus 1 tensor power, this is an ideal when you look at this algebra, the interval 0 to n plus 1 generated by all the sum. And this gives an exact sequence. And if you start with a nuclear system algebra A, then by weight equivalence, compact operators will be also nuclear. And then when you look at this exact sequence in an induction argument, you prove that each of these sums of these bn's, b0 to the intervals, they are nuclear. And the fixed point is actually the direct limit. So then you get nuclearity of the fixed point, and then for more general results on grading and pair bundles, you get nuclearity of the fixed. This is the basic idea. Now, I want to consider a correspondence is an action of the natural. We may do as a generalized action of natural numbers. In order to replace these natural numbers by a more general semigroup. And so we consider a semigroup with a monoid with an identity. Then a product system over P with correspondence over C star algebra A is a bunch of correspondence. So for each P, we have a correspondence where the correspondence associated to the unit element is the identity correspondence. And we apply multiplication maps, which are associative, which are isomorphisms of correspondence, when you take the tensor from P and Q and P. And this satisfies some conditions like associativity. Examples. First, if you take a single correspondence, this gives the product system over the natural numbers just by taking the uniform tensor product. And if you have an action of P on A by injective endomorphism with hereditary range, you can define a product system over P, where for each fixed P, we have as the correspondence the one I mentioned before. And you take as the multiplication the method which is actually implements from E tensor EP tensor EQ, the map actually is implemented by alpha P, by the endomorphism alpha P. And if you don't want these assumptions injective and imaginary range, you can still get a product system, but then it's over the opposite format. And also you can have product system coming, for example, from higher rank rounds. And now we can, similar for a single correspondence, we can form what we call the Fock space. So we take a new correspondence over A by taking the direct sum over all the EPs. This has the diagonal left action is again a correspondence over the same coefficient algebra. And we have actually a representation of the product system into the adjointable operators of the Fock space. Correspondence just representation just means that we have a representation for each correspondence EP, and they are compatible with the multiplication in natural sense. And the Toeplitz algebra is defined to be the sister algebra generated by the range of this representation, and has a canonical copy of the coefficient algebra. And you can also define an analog of the Kunz-Spinzer algebra, which also detects better the embedding of A. It's more like a cross product. And you always be, the reduced version will always also be a quotient of the Toeplitz algebra. And as Marcelo was mentioning, now there are complications coming from the semigroup side and also from the action from the product system. Let's mention some examples. One example, if we consider the canonical product system with one-dimensional hardware, so at each fiber we just put complex numbers, then use the Toeplitz algebra is exactly the Toeplitz algebra of the semigroup, as Marcelo was mentioning before. And now, if you want to enlarge the fibers and consider the action of the semigroup on this larger diagonal commutative sister algebra inside the Toeplitz algebra, and you do the covariance algebra, so what would be the Kunz-Spinzer algebra, you get a free analog of the Toeplitz algebra. And if you take the product system to the canonical fibers and take then the Kunz-Spinzer algebra, what you get is the analog of the Kunz-Spinzer algebra, what you get is an analog of the boundary quotient of the system. And here we don't have the group, we assume that P embeds in a group, and not necessarily the integers. And we always have, we replace the action of the circle that we had before by a coaction of the group containing P. And this gives to the Toeplitz algebra also a nice structure, a nice grading. So we have a collection of closest subspace indexed by the group, and the multiplication and evolution are compatible with the group operation. And if P embeds in an amenable group, so all this construction does not depend on the group, this is the algebra. And if P embeds in an amenable group, then the Toeplitz algebra is nuclear if only this fixed Toeplitz algebra is nuclear. And the question is when, in this case, nuclearity of the coefficient algebra then imply nuclearity of the fixed point algebra. And then whether P embeds in an amenable group or not, that's a different question. So let us consider the case of compact aligned product system over a widely same monoids, meaning that if there are two elements, they either have no common upper bound or they have a least. And in this case, there is a class of product system called compactly aligned, which they satisfy a nice, the Toeplitz algebra that has a nice structure because it's spanning by elements of this form. And so as Marcelo has mentioned, we can put all the annihilation on the right and all the creation operators on the left. So this has a very nice spanning set and then allows us to study better the Toeplitz algebra. So if you consider, for example, the product system coming from a higher rank graph, this corresponds to the graph being aligned. And as a consequence, the fixed point algebra will be a sum, will be again a direct limit of sub-algebras. And each sub-algebra is actually a sum, a finite sum of compact operators on which corresponds. And hence, in this case, you can say that nuclearity of the Toeplitz algebra of the fixed point is equivalent to nuclearity of A. So this structure has been considered in previous work of many people here, like Adam Sims and Naja and previous sources. And it's very similar to the argument in the case of a single correspondence. So now to consider the more general case. So our goal in this project was we wanted to say something when we have a product system which is not compactly aligned, even if you still have the assumption of the group to be Waterloo and or we want to just consider general classes and be able to say something. So here we have is the same notation as I was using before. So we consider words in the monoid. And this alpha dot is an element of the group. And we consider the reversed word. And for each word, we have a conceptual white ideal. And we consider the collection of all conceptual white ideals of the same group, which is this J. And for each word alpha, and choice of elements on each correspondence, then we have an element of the Toeplitz algebra. But now this again, if you fix a word, that can be many different elements. And so this gives a spanning set for the Toeplitz algebra, and also if the fixed point algebra will then be spanned by elements such that the word is neutral, meaning that the group element is the identity. And now we looked at the structure of this fixed point algebra, and it actually has a similar structure as in the case of Waterloo, but except that the algebras are more complicated. So we have for each S, we can consider the system algebra generated by all elements of the algebra corresponding to words such that the consortium white ideal is S, and words are neutral. And this gives a C-star to the algebra of the fixed point algebra. If your conceptual white ideal is P, this is actually just A. In particular, we always have conditional expectation, also the coefficient algebra A. And if you consider a finite collection, which is closed undertaking intersection, the sum is also to the algebra of this IS. And the fixed point algebra for this gauge collection is actually the limit taken by all increasing finite collections intersection rules. And in particular, similar as before, using some exact sequence, you can show that if each of these algebra corresponds to a conceptual ideal is nuclear, then the fixed point algebra is nuclear. So before in the semigroup system algebra, given a conceptual ideal S, the corresponding system algebra IS will be simply a projection in complex numbers. And here it could be complicated. And in some cases, you can go back and you have equivalence here. And then we started, our main motivating example was coming from this product system coming from actions of semigroups, iterative range, and injective. And we started looking by words that are symmetric. So if we start, look at a word, the one like P, and is symmetric. And actually, then you consider the collection generated by this word by taking concatenation and conjugation by other words. And we proved that if you have a product system such that the left action contains the compact operators of for each correspondence EP, and you fix a word in this collection, then actually the element, each spanning element in this algebra, you'll be acting on each correspondence on the top space as an element of A. So it's really acting as an H. And this assumption exactly came when we are looking at this product system from actions of semigroups. And then we show that if we assume that for every conceptual like ideal, then you can, this algebra corresponding to S is actually coming by compression of elements, string elements coming from these modes that are generated by math keywords, then we can prove the equivalence. Nuclearity of the coefficient algebra is equivalent to nuclearity of the fixed point algebra for the gauge correction. And if the group containing P is a minimal, then this is all equivalent to nuclearity of the large algebra. And all this condition here is giving us is that this algebra corresponding to the consensus ideal F is actually a quotient of some ideal in A. And hence, if here is nuclear, then the algebra is also nuclear. And of course, which class of examples we can have this, and we can show that this satisfies a very full product system, such that the left action contains the compact operators for every abelian monoid, and for every Balanced solitary monoid, and for every AX plus B monoid of an integral domain. This contains, for example, a full product system, full meaning that the right inner product generates the algebra. And this contains, for example, a product system of Hilbert bimodules, which are full on the right. And in this, all these monoids, they embed into amenable groups. That the Balanced solitary monoid embedded in an amenable group is a result of a student option in these cases. Yeah. So then in this case, you have equivalence between the two conditions. So these are all. Thank you.
Any questions for Camila?
How hard is it to check the first conditions?
So this one?
Yeah.
So we don't have examples where this is not hold, but I don't think it will be always true. Like in general, even for semi groups, CSR is not clear whether you can generate all the algebras this way. But it seems to me that if you have the product system is full on the right, and the semi group is somehow generated by a Boolean thing, then it seems that you can argue. Like in this case, you have a semi-directed parallel of a Boolean things, and this is commutative. And the Balanced monoid, you also have some sort of you have some generated by a Boolean, something acting as a Boolean.
Yeah, so how about the right angle arcing monoids?
Yeah. I suppose that would be true. I think I don't think we'll be in there. Because for free monoids, automatically compact align, right? And by arcing angle, I don't know if it's probably not automatic compact align. I think it should.
There are usual results from the possibility.
But you don't want to assume compact aligned, right? And the question is if other, like if it is a free monoid, then the product system will be automatically compact aligned because they are either comparable or not. But for the right angle, it's not the case. So you could have examples that are not compact aligned. I would expect that we could also show this, but I haven't seen.
Any last questions for Camila? If not, let's thank her again.